All right, guys, I know you're excited. We've gotten to the word problem section of chapter 4. So we're going to be talking about exponential growth and decay. So first we're going to talk about our growth models. And I just want to introduce a little bit of kind of vocab and notation to you. So we're going to be talking about equations in the form, or models in the form A equals A, little subscript 0, times e raised to the power k times t. This is kind of like the basic exponential function. So down here in this example, we're going to have a equals, and we pronounce this guy a naught. So that a with the subscript 0, we call it a naught. So that's what this whole thing is over here. So a equals a naught times e raised to the power 0.086640 times t. So in this example, that's what we're looking at. So we're given this rate k. That's that 0.086640 number. When we're talking about growth and decay models, whatever that coefficient is times t up in your exponent determines whether you have a growth or decay model. So if k is positive, you have a growth model, and if k is negative, you have a decay model. So in these first few examples, we're using this growth model. So we're modeling the growth rate of bacteria. So here the population of a certain bacteria grows at a rate modeled by the function that we already talked about before, where time t is measured in seconds. So I'm just going to make a note of that because it's a different unit. Normally we had years. Bacteria grow pretty rapidly, so now for this model, t is in seconds. And it says use this model to solve the following problems. And for all these examples in this section, by the way, we'll just go ahead and round our answers to the nearest whole number, the nearest integer. Not that those are interchangeable, but because we have positive numbers, they are. All right, for number 1, if there are 10,000 bacteria originally, how many bacteria will be present in 8 seconds? So we're given the numbers 10,000 and the number 8. 8 seconds means t is going to be equal to 8 in this example. And then it says 10,000 bacteria originally. That's what that A naught guy represents. So that subscript 0 represents a time of 0. So at time 0, what's our initial amount? So originally we have 10,000 bacteria. So 10,000 is going to be A naught. All right, so let's plug this into our model. So basically, we just have A left. I don't know what A, that accumulated amount, is. But I'm going to put in 10,000 for A naught times E raised to the power 0.086640 times T, which in this case is 8. All right, so we're trying to figure out how many bacteria we have after 8 seconds. And we'll just type this result into our calculator and then round at the very end. So when I'm accessing E, remember I'm going to hit my second key, and then I'm going to hit the natural log, the ln key, which has that little E superscript X above it. So I'm going to hit first 10,000, right? So 10,000 times, and then to access E, I hit second, and then my natural log key to pull up the E. And then mine goes right up into the exponent. If yours doesn't, if yours has E and then the little caret, like E and then a caret, then it'll probably start off with parentheses. Just make sure everything is written in parentheses and close those to make sure everything stays in that exponent. All right, so for me, I don't need the parentheses, so I'm going to just start typing 0.086640 times 8. That whole product is going to be up in my exponent, so I can go ahead and hit enter. And there's my result. And if I'm rounding to the nearest whole number, nearest integer, this is approximately 19,999 bacteria. Remember your units for your word problems. All right, so before we move forward into number 2, I also just want to point out, I know this model looks pretty scary. That's a super weird growth rate. The decimal's pretty bonkers. But this looks really similar to that PERT formula that we had before, right? So now just instead of P, we have A naught. We have that initial amount. And instead of R, our interest rate, we just have K for our rate. So it's that same kind of format. So I just wanted to point that out. All right, for number 2, if there are 5,000 bacteria originally, so that's going to be our A naught, how long, so that leads me to believe we're going to be looking for a time amount in seconds. How long will it take for there to be 320,000 bacteria? So that's going to be our accumulated amount of bacteria. So let's use this formula again. So now for A, I'm going to write in 320,000 equals my initial amount, 5,000, times E raised to the power 0.086640 times T. All right, so in number 1, it was just, do you know how to use your calculator? We just needed to perform that calculation. Now for number 2, we're going to need to solve for T, and T is up in the exponent. So we're going to need to use techniques from the previous section where we were solving exponential equations. So I'm going to use that method where we take the natural log of both sides. But remember, before we take the natural log of both sides, we want to fully isolate our exponential just to make our lives easier. So in this case, to isolate, I'm going to divide both sides by 5,000 first. All right, so let's see, 320,000 divided by 5,000. So that gives us 64 equals e to the power 0.086640 times t. We've got it isolated, so now we'll take the natural log of both sides, which allows us to use the power rule. So natural log of 64 equals 0.086640t times the natural log of e. And recall that the natural log of e is 1, so we basically just got that coefficient times t. And now to solve for t, I just need to divide by that lovely 0.086640 on both sides. All right, so we're ready to type this into our calculator. The natural log of 64, use the right arrow to get out of those parentheses, divided by 0.086640. I'm rounding to the nearest whole number, approximately 48 seconds. All right, on to number 3. If there are 500,000 bacteria after 4 seconds, how many bacteria were originally present? So we're looking for a naught. We don't know what that is. 4 seconds, so t equals 4. 500,000 bacteria is going to be our accumulated amount. So let's fill all that into our model. So now we've got 500,000 equals a naught times e raised to the power 0.086640 times t, which is times 4. All right, so in this example, we're solving for a naught. So basically, we just need to divide by that e raised to its exponent on both sides, and then we'll solve for what we're looking for. So I'm going to divide out e raised to the power 0.086640 times 4. E to the 0.086640 times 4. I know it looks crazy, but it's just like 2 times a and then dividing by 2. So we're dividing out that whole wackadoodle constant there. So let's type this very carefully into our calculator. 500,000 divided by, and then remember I'm going to use second and then the ln key to access e. Second and then ln, there's my e. And then all up in the exponent, use parentheses if you need to keep everything in the exponent, 0.086640 times 4. And rounding to the nearest integer, 353, 558. So approximately 353,558 bacteria were originally present.